Hey everyone, welcome back to Calculus 2. This will be lecture 3 of the course. And in this lecture we're going to talk about Riemann sums and definite integrals. So let's start by calling this lecture 1, section 1.3, Riemann sums and definite integrals. Okay, so we'll start with a definition of what we mean by a Riemann sum. Now, of course, this name Riemann, that's the mathematician Bernard Riemann, very famous mathematician. So the definition for a Riemann sum. Okay, and this is going to be very similar to what we saw in the previous lecture when we discussed area. And so there we had a nice definition, we had a definition of how to calculate the area using of a region under a curve by using a very precise sum and limits, and of the sum as the number of partitions grew to infinity. This is going to be very similar. It's a slight simplification of what we saw there, but I think you'll probably say, what's the difference when we get to the end of this one. So let f be defined on a closed interval AB. Okay, closed interval AB. And we'll let delta be a partition of AB. And we'll say it's given by, A equals x0, which will be less than x1, which will be less than x2, which will be less than ... less than xn minus 1, less than x of n equals b, right? So I've got basically a partition of n intervals on this overall interval from a to b, where delta xi is the width of the ith subinterval. Okay. All right. So I guess implicit in this is that the intervals do not all have the same width here, right? Because as you can say, where delta xi is the width of the ith subinterval. Now, if ci is any point in the ith interval, then the sum from I equals 1 up to n of f of ci times delta xi, right? Now notice here where xi minus 1 is less than ci, well, less than or equal to ci, which is less than or equal to xi. Okay, this sum is called the Riemann sum, of f for the partition delta. Okay, so there's our definition. Now, right, so a couple of things of interest here, right? So first of all, we're defining just delta to be any partition of AB into n intervals, right? Any being the key here. And therefore, delta xi is the width of the ith subinterval, and it's not implicitly the case that delta xi and delta xj are the same, right? So that's sort of an innovation here that may kind of sneak under the radar of if I don't explicitly call it out. And so the next statement would be then that the width of the largest subinterval, the width of the largest subinterval of a partition delta, okay, is called the norm. Norm, okay, of the partition. And it's denoted by the norm of the partition equals delta x equals b minus a over n. Okay. Okay. All right. So the number of here's the kind of the setup, right? So you've got n intervals, right, and each of them. So you have n intervals, and they're each going to have a certain width, right? Now, as the norm, right, meaning basically the width of the interval, as the norm goes to 0, right, what happens to the number of subintervals that are going to be needed to partition the region AB, or the interval AB? So as the norm goes to 0, the number of subintervals, okay, in the partition goes to infinity. Right? Now, hopefully that's sort of intuitive, right? So here's my xy axis. Here's my interval AB. Right? If I start with just that many, right, then the width is a certain thing. Right? Now, if the width, decreases, if, maybe it cuts in half, then obviously the number of intervals increases, right? And if it cuts in half again, obviously the number of subintervals increases further, right? So as the width goes to 0, n goes to infinity, n being the number of intervals. Okay, so this is so the mechanism here that we're looking at is going to be subtly different, right? We're going to define a definite integral using the Riemann sum version of things rather than the version that we sort of etched out in the previous example. But hopefully, having gone through the previous lecture and gone through the examples in that section, hopefully this isn't a stretch, right? This should be totally intuitive, right? Having gone through what we just went through. Okay. All right. So we're going to basically, what we're going to need to develop here is the idea of the definite integral. And kind of the backdrop to the definite integral is a particular limit. So let's talk through this limit. Now, this could get hairy. Warning, this could get hairy. It's not something that's, you can intuit what's going on with the definite integral without necessarily feeling great about this definition or about the following limit, but it can help, and some people find this extremely helpful. So consider the following limit. Okay, consider the following limit. So the limit as the norm goes to 0, the norm of the partition goes to 0, of the sum from I equals 1 to n of f of ci times delta xi equals L, right? So this is the Riemann sum here, and what we're doing is letting the norm of the partition go to 0 and letting the and then summing over the Riemann, and then considering the Riemann sum, right? And so if we say that this is equal to L, what does that mean? What does that mean? Okay, let's copy this over here to the next page. So the limit as the norm of the partition goes to 0 of the sum I equals 1 to n of f of ci delta xi equals L. What does this mean? Well, to say that this limit exists, what does it mean? So to say that this limit exists, okay, means, right now we've seen limit theorems, we've seen limit definitions in the past, and limit theorems, we haven't probably got as much experience with them as we could have had, but this is calculus, just basic calculus. So once you get into analysis, these types of things will be done. You'll be messing with this every day. But to say that this limit exists means that for all epsilon greater than 0, okay, so any positive quantity given, there exists a delta greater than 0 such that every partition with the norm of the partition being less than delta will imply that the value L minus the Riemann sum is less than epsilon. Okay, so this is the idea here, right? So basically, if you give me an epsilon greater than 0, I'm going to be able to come up with a delta greater than 0 such that any time the norm of the partition is less than delta, right, i.e. the width of the width of the largest subinterval is less than delta, then the value L, the limit value, minus the Riemann sum, minus the estimated area, is going to be less than epsilon, right? I can get within epsilon of the true area by just making the partition fine enough, basically, is the idea. Okay, so that's what this beautiful little ditty is telling us. Okay, now this is, it's similar to the epsilon delta proofs that we saw back in Calculus 1. Of course, it's more complex because it involves a Riemann sum, and it involves not just, being within delta of a particular point, but instead having the width of, having the norm of an entire partition be less than a certain delta, right? So it's a little more complex, but it's the same idea, right? Same idea. If I want a certain amount of precision, I need to be able to find a partition that guarantees that precision. That's kind of the idea. Okay, so next, that's where we'll leave it. I do encourage people to dig into this more and make sure, to try to understand it. It's not absolutely crucial for Calculus 2 that we be fluent in epsilon delta proofs, however. So let's go ahead and define the definite integral quick. So this is going to be a definition, kind of an important one. This will be the definite integral. Okay, so let f be a function defined on a, b closed interval, and assume that the limit, right, the limit we just looked at, the limit as the norm of the partition goes to 0 of the sum I equals 1 to n of f of ci delta xi exists. Okay, so f is a function defined on the closed interval ab, and assume that this limit exists. Then we say f is integrable, okay, integrable on AB, and the limit is denoted by, so here's what we'll say. It's basically exactly the same thing, but I'm going to write it again. The limit as the norm of the partition goes to 0, sum I equals 1 to n of f of ci delta xi. Okay, so this limit is equal to the integral from a to b of f of x dx. Okay, and so this limit, right, this limit is called the definite integral of f from a to b, from a to b. Right, that's kind of the wording there. Okay, from that. So that's the definition of a definite integral. So so remember, previously we had the indefinite integral, which we defined as the operation of identifying the general family of antiderivatives for a given function. Here we're defining what's called the definite integral. So we have indefinite integral, now we have the definite integral, and it looks totally different. This is a completely different, seemingly completely different sort of thing, right? So here we're talking about area, right? We're talking about the function evaluated as ci, which kind of intuitively represents a height, and delta xi representing a width, adding them all up, and then doing that at the limit where, the partition width goes to 0 and in goes to infinity, right? So seems like a completely different idea, and indeed it is not a completely different idea. They are connected in a very interesting way, and we'll get to that. But so notice, it's no coincidence. So it's no coincidence that the integration symbol is used for both definite and indefinite integrals. Okay, it's no coincidence, obviously. They're both called integrals too, so that would make sense. But we'll see how these connect actually in the next session. Well, we'll see in the next lecture. Okay. But it's important to notice the differences here. So a definite integral, what is a definite integral? Well, it's a number, right? It's a number. You're going to get some number out of this process, right? Similar to the examples we did in the previous lecture where we calculated the area and then we took the limit. We ended up with like numbers like 5/6 or something, or 2/3 or 8.4. A definite integral is a number. An indefinite integral well, this isn't a number, it's a family of functions. Big difference, right? So this is a family of functions, right? Remember, the definite integral one of the things that you can notice is it didn't have these bounds on it, right? It was just the integral times the function. It was the integral of the function, right? There were no upper and lower bounds here on the notation, and so that's a big clue, right? So if you have these bounds in place, you're dealing with a definite integral. If you don't, then you're dealing with an indefinite integral. And so they're totally different things, though, seemingly. I mean, on the surface anyways, a definite integral produces a number. An indefinite integral produces a family of functions. Okay? So, so I guess one thing to notice that I didn't write, I didn't explicitly state, what I'll state now, is that when you have a definite integral like this, right, a and b are called the lower and upper limits respectively, right? And b is called the upper, right? So just terminology there. Okay, good. Yeah, and so we'll come. We'll come back to this in 2 seconds, but let's toss out a theorem here quickly that we may need. Okay, so this is continuity implying integrability. Continuity implies integrability. Okay, if a function f is continuous on a b closed interval, right? So if it's continuous on all those values, then it's integrable on those values. Nice, right? That's convenient. So basically, any continuous function we can integrate. If any function that's continuous on AB can be integrated on AB, definite integral, right? So that means we can calculate areas of functions in a very nice way. Okay, let's do an example here. Okay, let's example. Evaluate the definite integral from -2 to 1 of 2x dx. So this will be kind of using the Riemann sum approach here. And so let's say delta xi equals, well, delta x equals b minus a over n. All right, so just kind of plugging in a delta x here. So that'll be 1 minus -2 over n, so that'd be 3 over n, right? Okay, so we'll let that be our delta xi. And ci we can set up to be basically a plus I times delta x, right? Simple, kind of, that's how it'll be. We'll just set a equal to, we'll set ci equal to a, which is the lower end point, plus I times delta x. Okay, which in our case, in the case of this exact example, would be -2 as the lower bound, plus I times 3 over n. Okay, and so then we can calculate this integral, right? We can calculate -2 to 1 of 2x dx. That'll be equal to the limit as the norm of the partition goes to 0 of the sum from I equals 1 to n of f of ci times delta xi, okay, which is, let's plug these values in, the limit as, now, so when the limit as the norm of the partition goes to 0, right, that's equivalent to saying the limit as n goes to infinity. Remember, we had that discussion briefly sort of at the beginning where we said the norm going to 0 if and only if n goes to infinity, right? That's kind of the sort of one of the main things that we sort of set up at the beginning. I guess we kind of glossed over that, but that's the idea. Well, we talked about it. We definitely talked about it. So there's that, and then so basically this gets rewritten as the limit as n goes to infinity of I equals 1 to n of f of ci delta xi. Okay, and then let's plug in our values. The limit as n goes to infinity of the sum I equals 1 to n. Now f of ci, so here's your ci right up here, right? So f of ci will just be 2 times whatever ci happens to be. So it'll be, 2 times. 2 times, and then it's -2 plus 3i over n. Okay, and then times your delta xi, which is 3 over n. Okay, and we can sort this out pretty quickly, right? So the limit as n goes to infinity, let's pull out a 6n. 3 times 2 is 6, and there's the n. And what do we have left? -2 plus 3i over n. Okay. And so limit n to infinity of 6n. Okay, now we can just kind of toss these numbers in. Now we talked about this last week, but you could break this sum up, right? So it'd be the sum I equals 1 to n of -2 plus the sum I equals 1 to n of 3i over n. But I'm just going to kind of do it in one step. And so this would be -2 times n. So you get -2n there. And then this one you would be plus 3 over n. And then this would basically be the sum I equals 1 to n of just I. So that would be n plus 1 over 2. Right, like so. And so that's that's a pretty good point to be in. Now we can do some work to this. We can clean this up. So the limit is n goes to infinity of, I'm gonna just kind of, we can finish this. So it'll be 6 over n, and then -2n plus 3 halves n, and then I'm going to need another page here, aren't I? Shoot. Okay, so let's just throw us on the next page. And we can easily set this up. So I've got -2n plus 3 over 2n, and then this will be n squared plus n. Probably could have done that in one step. That's okay. It's good to take your time, right, when you're doing this stuff, especially if you're learning. So you'd have 3n over 2n, 3n squared over 2n, plus, let's see here, -2n plus 3n over 2n, plus 3n over 2n. Okay. Okay, and the 6n is outside here. Okay, good. Okay, so then this would be the limit as n goes to infinity. Now all of this is gonna be a lot of canceling, so we get -12 here, and then we get a 9, right? 6 times 3 is 18, divided by 2 is 9, and the n's all cancel. And then down here, we're going to have an n, and then an n squared, so it'd be plus 9 over n. Okay, can we evaluate that limit? Oh, you betcha, right? So this will be -12 plus 9. This is going to 0 as n goes to infinity. And so we get -3 as our integral, right? So long story short, the integral from -2 to 1 of 2x dx is -3. Okay. Okay, so there we go. So now let's jump into a theorem that's going to kind of tie this lecture 100% to the previous one. Okay, this theorem is going to be the connection of the definite integral to the area of a region. Okay, super important. If f is continuous, and non-negative on the interval AB, okay, then the area of the region bounded, okay, of the region bounded by the graph of f, okay, the x-axis, and the vertical lines x equals a and x equals b is given by okay, very good. So in a picture basically means this. I've got some function here, f, I've got some a, I've got some b. This area is calculated using this integral. this definite integral. All right, very cool. So that is, like, this is sort of the kernel, I would say, of, well, I don't know if it's the kernel, but it's certainly a key fact from calculus, and from specifically the integral calculus, which is what we're in calculus 2 now. So let's see some examples here. Let's see what this looks like. So let's look at like basic shapes first and see what they look like as an integral. So what about like a square or a rectangle? I'm saying rectangle probably. So if I have my xy axis, right, and I've got some region, say 1, 2, 3, 4, 5, 6, and I've got some, maybe we'll say 1, 2, 3, 4, then the area here, that area from 1 to 6 under the line 4, that's a rectangle, isn't it, right? So it's 4 high, 6 wide. That's equal to the integral from 1 to 6 of 4 dx. Okay, so that would be the area of a rectangle. Square would be very similar. I just obviously kind of bring this back a couple. Okay, so that's the area of a square of a rectangle. Okay, so just basically a constant. Integrate a constant, you get a rectangle. All right. What about like a trapezoid? And let's say we've got a function like this, maybe 1, 2, 3, maybe 1, 2. Okay, and let's just say this kind of comes down like this. Here's your function. Right, and so you're going to get a trapezoid in here. Right, that's, a four-sided shape. The two edges are parallel and the other sides are arbitrary. But yeah, so this would be the line f of x equals x plus 2 right here. And so then the area of this trapezoid could be calculated as the integral from 1 to 3 of x plus 2 dx. Right? So this particular trapezoid could be calculated. The area could be captured using this. Okay. What about another example? What about like a semicircle? Okay, so like a semicircle. So let's say we've got our xy axis. So you got 1, -1, -2, 1, +2, and then 1, 2 here. And so let's say you've got a semicircle. This will be a bad drawing, but you can imagine this is, I think we'll say that's perfectly circular, semicircular. So then this function here would be 4 minus x squared square root. Okay. And so then this area of the whole thing here we could capture as the integral from -2 up to +2 of this function, 4 minus x squared dx. Okay, so this would be the area of a semicircle. Okay, very good. All right. So, how we go about actually calculating these things, we'll get to, don't worry. But let's start, before we do that, let's iron out a few properties of integrals and a couple special integrals. And then next time, I believe, we'll get into the fundamental theorem of calculus and we'll start actually calculating what these integrals are all about, how to actually get to these numbers efficiently without having to resort to the limit as the partition goes to 0 of the Riemann sum. So a couple of special integrals, two of them in particular, two special definite integrals to look at. Okay, the first one, if f is defined at a specific value of x, so if f is defined at x equals a, right? So a specific value of x, then the integral from a to a of f of x dx, right? So the integral from the point A to the point A, i.e. having gone nowhere, the integral over a single point is equal to 0, irregardless of what f happens to be, right? So anytime you have, you know, a function and at one single point A, then you can think of it as this, like literally the area under that curve at that one single point is 0. Okay, now hopefully that's intuitive, right? If you just think of the area here, you've got a height, but your width is 0, right? So the area is naturally 0. Okay, so hopefully that's not too big of a stretch. The second one, the second special integral, so let's say if f is integrable on the interval a to b, okay, a up to b, a, so i.e. a is less than b, right? So key. Then the integral from the integral from b up to a, well, actually you'd say b down to a, actually, wouldn't you? Is equal to the negative integral from a to b of f of x dx. Okay, so this one is a little bit stranger, right? So if you have an interval a to b, a less than b being the implication there, right? Then, well, I guess a be less than or equal to b, right? It could be a single point, in which case this would be true, in which case this would also be true. So the integral from the top down to the bottom is going to be equal to the integral, the negative integral of a up to b. Okay, so the way we know how to calculate these integrals is from the lower value up to the higher value. So if you have something like this, it's not meaningless. You just have to kind of switch it over to this other more interpretable form. So, and in doing so, you can flip the limits and put a negative sign out front. We'll get into examples of this in a few where this is useful. Actually, it'll come up very frequently, actually. We'll see it quite a bit. Let's do a couple of examples just to iron these out, just to, well, send them home, basically. So evaluate, what about the integral of sine x dx from pi to pi? Well, hopefully we don't have to worry too much about this one, but this one is 0, right? We don't even have to look at the function, right? It's just pi to pi, it's 0 automatically. Okay, what about integral from 3 up to 0 of x plus 2 dx? Okay, so this one, your lower bound is further out on the real number line than your upper bound, so this would be equal to negative integral from 0 to 3 of x plus 2 dx. Now, we didn't actually figure this one out, but this is that trapezoid, isn't it? This is that trapezoid. 1, 2, 3. 1, 2. So this would be that trapezoid that looks like this. Okay. Can we figure out what this area is? Well, I mean, let's say we don't know how to integrate, we can figure it out just using the old trapezoid rules, right? So the area here is equal to 1/2 3 times 2 plus 5, right? And so that would be equal to, let's see, 3 times 7 is 21 on the top, 2 on the bottom. There we go. Right, so this is 1/2 3, right? So 1, 2, 3, it's the height, and then it's 2 here and 5 here. So this one is 2, this one is 5, this one is 3. 3 is the height, and then it's always 1/2, right? That's sort of the formula for the area of a trapezoid. So the area of a trapezoid in general, area of a trapezoid in general is 1/2, well, it's different ways to write it, h over 2 times a plus b, right, where your trapezoid is like this. Okay, and so that's kind of what we did. So then basically this integral here from 3 down to 0 of x plus 2 would be equal to negative 21 over 2. Okay. All right. So this is, kind of a contrived example where we're just kind of looking at these bounds and flipping them and putting the negative sign on. Okay. Very good. Very good. So those are a few examples using those special integrals. What about what happens if we can we add integrals? We can indeed. So if f is integrable on an interval ab, okay, then the integral from a up to b of f of x dx is equal to the integral from a up to c of f of x dx plus the integral from c up to b of f of x dx, where a is less than or equal to c is less than or equal to b. Okay. Okay, so c is some number in between. Now, hopefully this is intuitive. I mean, this basically kind of tells you that the area works in the normal way for when you're calculating them using definite integrals like this. So say you got some c in here, right? Well, the overall area, right, that's this, that's the whole thing, is equal to this plus this, right? So it'd be this part here plus that part there. And if you add them up, you get the whole thing. It's very intuitive. That part's very intuitive. Good. Intuition is nice. It's nice when your intuition matches the theorem you just read. Let's see an example. Let's look at the integral from -1 to 1, the absolute value of x dx. So what does this function look like? Well, it's one of those absolute value functions, isn't it? So it kind of looks like this and like that. So let's say you've got -1 here, +1 there. So we're interested in all of this area right there. Okay, well, we don't know how to integrate a definite, we don't know how to integrate the absolute value of x yet, right? But we do know this. We do know that the integral from -1 to 0 of absolute value of x dx plus the integral from 0 to 1 of the absolute value of x dx is equal to the integral we're looking for. And we know that the integral from -1 up to 0 of the absolute value of x dx must be equal to, this must be a negative x, right? Right, because it's absolute value and these are all negatives, right? So you're plugging in a negative and you get a negative times a negative, negative, positive. And the same thing over here, except it's going to be positive x. So we know that's true. So what's this piece and what's this piece? Can we figure it out? Well, we haven't really talked about how to like actually evaluate integrals yet. But this is just a triangle. And this is just a triangle. Right? Think of these triangles as, you got two triangles here. The bases are both 1, right? What's the height? Well, this is just the function x, right? So the height is 1 also. And this is just the function x, so the height is 1 there. Right? So what's the area of these? Well, each of them is going to be 1/2 base times height. So 1/2 of 1 times 1. So 1/2. So this is just equal to 1/2 plus 1/2, i.e. 1. Right? And so so basically we just use the area of a triangle, but in order to do that, we had to know that we could break this into two pieces. Right? Which we can. That's what the previous theorem just told us. Excellent. All right. Okay, and a few more properties, and then we'll be ready to really jump into it. Okay, a few more properties. Let's say if f and g are integrable on a b closed interval and k is some real number, constant, then k times f and f plus or minus g are also integrable on a b. Okay, now let's itemize these a little bit. So the integral from a to b of k times f of x dx. So k is a constant, remember. And so just like with the indefinite integral, it's okay to pull the k out of the integrand and proceed without it, and then at the end multiply everything together. And similarly, we solved this same thing for indefinite integrals as well, where if you have f of x plus or minus g of x, right, it's fine to break the integrand. That's what this piece here is called, the integrand. It's fine to break it apart. So it'd be a to b of f of x plus or minus, well, dx dx plus or minus a to b of gx dx. Okay, so you can just do them in two parts. That's nice, right? Very nice. Okay. All right. So here's an example. A very contrived example, but it gives you the necessary. So let's say that the integral from 1 to 3 of x squared dx is 26 over 3. And let's say that the integral from 1 to 3 of x dx is 4. And let's say that the integral from 1 to 3 of 1 dx is equal to 2. Okay, so you've got basically this, and that. So you got these three facts, we'll say in air quotes. Let the following information be given. All right, so if that's given, then evaluate the integral from 1 to 3 of negative x squared plus 4x minus 3 dx. Well, we have no idea how to do this, but we do know that we can take an integral like this and we can break it up into a bunch of pieces, right? So the integral from 1 to 3 of negative x squared plus 4x minus 3 dx equals, right? We can break it first like this. right? We can do that. That's what the previous theorem just told us. F of x plus or minus g of x can be broken apart, evaluated separately, and then recombined. And further, the constants in front can be pulled off. So this would be negative 1 to 3 of x squared dx plus 4 times 1 to 3 of x dx minus 3 from 1 to 3 of just dx. So that's an implied 1, you know, the constant 1. All right, and so maybe I should put brackets around these just so it's clear. Right, this is the information that's given, right, what these three are equal to. So this is going to be equal to negative, and I just got to look up top here, 26 over 3 plus 4 times, and what was the x? Just 4, minus 3 times, and then this integral, just the integral from 1 to 3 of dx was 2. Okay, and so you can crunch all of those numbers together and you get 4/3. 4/3, so kind of a, well, very much a contrived problem, but just shows you that, you know, integrals that are more complicated, you know, like this, more complicated functions can be broken down into more simplistic functions, right? In the same way that we could do this same thing with differentiation, right? We could take a polynomial like this and break it down into 3 different derivatives real easily. You know, evaluate the derivatives and then recombine. So it's the same exact idea. Okay. All right, and now the one last thing, and then we'll end this lecture. This is the a theorem regarding the preservation of inequalities. So 2 parts to this. If f is non-negative on AB, then 0 is less than or equal to the integral from a to b of f of x dx. Okay, so basically any function that, you know, is non-negative on an interval is going to have a positive derivative, positive slope. You do run into negative slopes, and we'll talk about this more later, but if, for example, your function was down here and you want to know this area here, then this would be negative because it's below the x-axis. This one is positive, though. And we'll get into this example more specifically later, but the idea is this, right? The idea is that functions that are positive will have positive areas, okay? And that's all this is saying. And then a second part, which I think is probably even, you know, that one is you gotta kind of like buy that functions have negative areas when they're below the x-axis. This one is more straightforward, doesn't require a whole lot of buy-in. If f and g are integrable on an interval AB, closed interval AB, and f of x is less than or equal to g of x for all x in AB, then what do you think's going to be the case? Well, then the integral from a to b of f of x dx is less than or equal to the integral from a to b of gx dx. Right, so these areas just preserve you know, basic inequality principles, right? So that's nice. So if I have some function f like that and some function g like that, you know, and I'm interested in a to b, well, then it's rather obvious, I hope, that this is the area of G, the area under G, and this is the area under F, right? And so the area under G is greater than or equal to the area under F, right? That's visually very intuitive. You could look at that and say, yes, clearly that's going to be larger. There's a whole gap here, right? So this is all the extra area that's under G that isn't under F. Okay. So that's all. I mean, I know sometimes some of the theorems you go over, like, well, that's completely obvious. It's important to state the obvious in mathematics. If you haven't noticed yet, it's very important, actually. And, you should never assume anything. I mean, you can assume things, but make sure you know what you're assuming, right? That's kind of the name of the game with math. Assume X, Y, Z is true, then such and such follows. So even though something is patently obvious like this, you definitely want to call it out and state it, because it will come up in non-obvious ways later on. Okay, so that is it for this section. Now we covered a lot of material here. We talked about the Riemann sums and the definite integrals, defined both of them in one go. And next time we'll get into something called the fundamental theorem of calculus. And from there it will be off to the races regarding integrals, and we will figure out how to evaluate integrals, both definite and indefinite, using a variety of techniques. And we won't have to resort to definitions and limits. We'll just be able to use great, handy, amazing little theorems to get to the finish line much quicker. So I'll leave it at that, and we'll talk to you all next time.